All right, so here we're trying to simplify each expression. So in this case, we have variables as well, so we can't evaluate everything because we can't evaluate all the variables if they're unknown. So that's just the difference in directions. But we still want to try to simplify, get into simplest form. Okay. So number 12 this time, unlike number 11, this time we do have like bases. So we can actually combine these exponents by subtracting, right? So I can get x to the, and then I have 2/3 minus 1/4, right? So 2/3 minus 1/4, little mental math here. Get a common denominator. So we'll multiply by 4 on top and bottom here, multiply by 3 on top and bottom here to get the common denominator, which is 12, right? Which is the least common multiple between 3 and 4. So I get 8/12 minus 3/12, and that gives me 5/12. Okay, so that's my new exponent here. And that's as far as we can go. 5/12 is reduced, x to the 5/12, so we can't simplify that anymore. We could put in radical form, but we'll just leave it like that. All right, now, and generally that's the rule of thumb, is if you're given something in radical form, express your answer in radical form. If you're given an answer in exponential form, then express it in exponential form. All right, number 13. So here we have power rule, right? And we've used power rule before in some of those last examples. This kind of naturally comes in. But here we have u to the, and then I'm going to multiply 1/3 multiplied by 4/5, right? 1/3 times 4/5. So remember, when you multiply, you can cross cancel if you see anything to cross cancel, but generally just multiply straight across because there's nothing to cancel here in this case. So 1 times 4 is 4. 3 times 5 is 15. So we end up with 4/15. Can't simplify that. So we just leave it like that. All right, now 14. Here's one place that rational exponents come in handy, because we talked about we can only multiply radicals if we have the same index, right? So remember, with multiplication, you can have different radicands. You just have to have the same index. With addition, that's when like radical expressions have the same index and radicand, okay? So now these ones happen to have a 12 in the radicand, but this is 12 cubed, and this is just 12 to the first, right? So if I want to multiply these, I need the same index, right? And they don't have the same index. So what I can do instead is I can just convert these to exponential form. So I can make this 12 to the 1/2, right? So this is 1, and this is an invisible 2, right? So it's 1/2. And then I can multiply that by 12 to the 3/5, right? Okay, and now since the bases are the same, all I have to do is just add those fractions, right? You can use the product rule. So I can get 12 to the, and then I can just, in my head or on paper, do 1/2 plus 3/5, get a common denominator, which in this case would be 10, so I multiply by 5 here on top and bottom, and 2 here on top and bottom. So we end up with 5/10 plus 6/10, and that gives us 11/10. Okay, now remember, I did tell you that when you start in radical form, then you usually want to express your answer in radical form. So I'm going to convert this back to radical form. So it's going to be the blank root, and the index there is going to be 10. So it's a 10th root of 12 to the, and then I'm going to put that 11 back inside as the exponent. Now this one we do want to simplify, right? It doesn't just say convert, it says simplify. So if I have 12 to the 11th power, I have one set of 10 with one left over, right? So I have one set of 10 12s. If I listed this out, it would have to be 11 12s. So I have one set of 10 that I can group together and pull out 1, and then I have 1 12 left over. So that I'll leave that invisible 1 there, okay? So it's 12 times the 10th root of 12 is the final answer there. All right. So that's how you, if you're ever wondering what do we do if we're trying to multiply radicals that don't have the same index, then you can convert to exponential form. You can add the exponents, or simplify depending on what the case is. If the base are the same, you can just add the exponents. Okay, and then you can go from there. All right, now number 15. Now here, I know since these are the same, I can just bring out an a, right? So I can bring out an a. But on the inside here, I have 49, which is 7 squared, and then I have b squared, right? So if I put this in exponential form just for a second, this would be, I'll do the a as well. So this would be, let me see. So this would be 7 to the 2/8, right? A to the 8/8, b to the 2/8. All right, if I put this in exponential form. So I'm putting these exponents in the numerator, right? And then I'm putting this index in the denominator. All right. And then those can all be simplified, right? 7 to the 2/8 is the same as 7 to the 1/4. A to the 8/8, that's equal to a to the first, right? And we just talked about that's how it comes out, or that's another justification on why it comes out. So what I'm going to do here is, these are both to the 4th power, so I'm going to put them inside the 4th root, and then the a is going to come out, right? So my answer will be a on the outside, and then I'm going to have a 4th root this time of 7b, right? 7 to the 1st, b to the 1st, because of these, but I'm going to leave those ones invisible on the inside. Okay, so that's how we simplified. So we simplified from an 8th root down to a 4th root because we could reduce, right? So basically, just when you're thinking of these radical terms, remember that they are equivalent to rational exponents. And so if you have a situation where you have a common factor between all the exponents on the inside and the index, then you can reduce those exponents with the index, and you can get a smaller index, a smaller root. Okay. All right, and that's it. So let me know if you have any questions. Bring them to class, write them down in your notes, email me, and we'll see you tomorrow, and we'll get some more practice on these and get some more questions answered. Or maybe I'll see you today, depending on when you're watching this, right?